In this video, we're going to expand the linear regression model to more than one variables. We started off knowing the average monthly temperature and the pounds of steam used by the factory. And recall that we graphed that variable when we graphed those points, and then we could put a trend line right through there, and we know that that's the equation. And that is the predictive model that we have built to predict the amount of steam that was used. But let's now expand this, because sometimes you got more than one variable. So let's go over here and let's now expand to two variables. So now we know that the average temperature in the month was 35.3 degrees Fahrenheit, but we also know that the factory was open 20 days. So in this case it was open 20 days. Down here it was only open 11 days. Over here it was 23 days. So if I know how much or how long that the factory was open, it's going to obviously have an effect on how much steam that the factory uses. So of course, it's not so easy to graph this. If it's two dimensions, we know the amount of the temperature and the amount of steam used. This is easy to graph. When we start getting into more than one variable, it begins to be a bit more tricky to do. I suppose we could do this with a three-dimensional graph, but then when you get beyond a three-dimensional graph, it's not so easy. So what you would probably need to do if you want to visualize this data is to do a series of two-dimensional graphs and explore the data that way. And that's how it's done in a real-world situation when graphing is done. But let's just dive into this, and just using common sense, we can expect that the amount of days that the factory is open is probably going to be predictive of how much steam that they use. So we're going to just assume, we're not going to do any exploration of this data, we're just going to assume that this is a predictive variable, and we're going to build a model. Now how do we do this? Now there are very simple formulas for a two-dimensional graph, and we didn't go into those, but there's something that you can look up on the internet very simply. You know, you can look this up anywhere, and the formulas for calculating this line, there's just a couple of formulas, and it's just a matter of adding a lot of data together and doing some division, and you get this. But when you start getting into two dimensions, we now have to move into matrix algebra, which is really beyond the scope of this course. But I want to very quickly show you two good resources that if you want to, for the interested student who really wants to know the math behind doing what we're about to do, I would recommend that you get this book right here. It's called Applied Regression Analysis by Draper and Smith. And incidentally, Draper and Smith is the source of the data set that I have. Norman Draper and Harry Smith, this is a classic book on linear regression, and it shows you how to do the linear regression when you have more than one variable. It involves matrix math, and they were the ones who had this steam data set. If you want to also understand the linear regression but not crawl into the weeds so much, I would highly recommend this book, and it's not a joke, it's really called The Cartoon Guide to Statistics. It's a very simple book, but it explains statistics to non-statisticians really well. So I would highly recommend this. But neither one of these is within the scope of this class. The purpose of this class is to give you an idea and understanding of what this technique is giving us. So now let's go and build a predictive model or a linear regression model to decide how much steam the factory is going to use. So we come over here to our Data tab, and we're going to click on Data Analysis, and there's regression, so we want to do a regression. And the first thing that we're going to do is decide on where to put our output, so let's put it right there. Or let's put it up here. Okay, now let's select our target variable. We want to predict the steam usage. So we come over here and we just select it, and we're done. And then we're going to come over here and get our input variables. Now, right now, it's just set to this one variable, but now we're going to expand it to two variables. And the labels are checked, and let's hit OK. And voila, there we go. So now what do we have here? Well, you can see that our predictive model is that the amount of steam that is going to be used in a month is going to be equal to 0.202 times W. So basically every time the day is every day that the factory is open, you're going to use 0.2 more pounds of steam. And then if we have for the temperature, the more for like 35.3 degrees, it's going to be the temperature times this right here. And then we add 9 pounds to that. So these are the coefficients that we're going to use to predict the steam usage. And let's take a look at the p-values. So recall that the p-values are simply what's the probability that this is a bad variable, or not bad, but a variable that probably shouldn't be in the model. That's a better way to put it. I don't want to say bad because you might want to leave the variable in the model even if it has a high p-value. So it's not bad to leave it in. However, this is just going to suggest that that the variable might not belong there. So these p-values are suggestive that all of these variables are significant and should be in the model. Furthermore, we take a look at our f value here. So this is the what's the significance, or how good is our model? And again, this is a very small number. 10 to the minus 10 power is a really small number. So the chances that this is a bad model are really small. So that's another the significance of the model is going to be this is clearly a good model. So lastly, we look up here at the r-squared value. And this has an 84% r-squared value. Now, this is a higher number than when we looked over here. With one variable, it was 71%, and now the number, when we added a second variable, it's 84%. Well, 84% is bigger, but that doesn't necessarily mean it's a better model, because what you're going to find out with linear regression is that the more variables you throw at the problem, the better this r-squared value is going to be. So what they do in statistics is they have what's called an adjusted r-squared, which means that we're going to look at your accuracy, but we're going to penalize you for the amount of variables in the model. The more variables you get, we're going to kind of ding you a little bit. So we're going to there's going to be a penalty for having more variables in the model. So when I want to look at the accuracy of a model or compare it, so which is a better model, this guy or the other guy, what I can do is look at the adjusted r-squared, and you can see that this is 83%. So this one is now, I'm looking at the whole accuracy. However, I'm going to penalize with and the formula is not really within the scope of this class, but there's a formula to look at the adjusted r-squared. So I'm going to adjust this accuracy and penalize my model for having 3 variables, 1, 2, 3, instead of 2. So this is 83%, and let's go back and look at this guy, and it's 70%. So clearly adding that second variable has now improved my model. Now let's just finish the exercise up by predicting the amount of steam that we're going to use in the factory. So if I were to say something like, with this formula right here, I can say that the amount of steam that they will use will be negative 0.07239 times the average monthly temperature plus 0.202815 times the number of days that they were open plus 9.126885. Voila. So we would predict that we will use 10.6 pounds of steam, and the real answer here was 10.98. So let's just do what we did before. Calculate the errors here, and equals this guy minus this guy, and let's also come over here and grab the average error squared, because that's what we will be looking at in a real world situation. So let's just take these guys all the way down and see what the average error squared was. And heck, let's just grab this guy again. It was 18.2. Let's see what it is now. Whoops. There. Now it's 9. So we've obviously decreased the average error squared on our data set. Again, this is on the training data set, not on a holdout data set. Now, let's just for fun, we can make some predictions going forward. We could say something like, what if we know that the temperature is going to be 90 degrees? Well, we would expect to use 7 pounds of steam that month. But now let's just get a little bit crazy here. Let's say we have 90 degrees out and the factory is closed, and it was closed all it was just closed the whole month, and it was 120 degrees out, really, really hot, or 150 degrees. Suddenly, when we get to some very extreme values, you'll notice something. You can get some values that don't make sense. You can't use a negative amount of steam. Of course, 150 degrees out, that's not going to happen. However, let's just buy the premise that it did happen. You now get a negative amount of steam. That's not possible. You're not going to show up on Monday morning and find more steam in the plant than you had when you left. It doesn't work that way. So here's another thing that you're going to need to know, which is that you are allowed in a predictive model to exercise common sense. So I could do something like this. I could just tell Excel, give me the maximum value of 0 or this number here. So if it ever is negative, Excel is going to say, nope, you can't be negative. It just has to be a 0. So you are allowed to exercise common sense. You might even say that there's a minimum value. I mean, maybe your steam factory cannot use beyond 20 pounds of steam in a month. I don't know. But you're allowed to exercise common sense when you're building these models, or when you're actually using them. Again, the formula is not sacred. It is a tool to be used, and if the tool is giving you a strange result, you are allowed to adjust it. Again, common sense applies. If it is illegal for you to do that, like let's say you've got some medical study going on, you can't do that. I mean, you'll have to follow the laws and the regulations. But if you're using this for a business purpose, don't look at that number as something that cannot be altered. You have to exercise common sense when you're doing predictive modeling. So let's finish up with one last exercise. Let's create a random variable here. We're going to call it random. And so we're going to use the random function here in Excel, random. And see, that gives us a random number. So we're going to do that, say, times 10. And it's going to give us a random number. And let's just go all the way down here. So we know that this variable is not predictive of the steam use because, again, it's a random number we're pulling out of a hat. So let's do the same thing that we did before, and let's build ourselves a predictive model. So let's come over here and do this, regression. We're going to put it right here. And let's go over here. Now the y's are going to stay the same. The x's are going to be these guys right here. We hit that, and we still have the label, and we hit OK. Now, let's take a quick look at this, and you see that we have 3 variables in the model. We have the random one, or actually 4 counting the intercept. We have the random variable that we know is not predictive, the w and the x, and this guy right here, which is the intercept. So these are the variables if we wanted to build predict how much steam was being used. These would be the variables we would have. But let's take a look first of all at the p-values. Again, these first 3 guys that we know are predictive already still have very low values. So the probability that we should take them out of the model is really small. So we would probably want to leave them in. So we're going to leave these guys in. But let's take a real quick look at this last guy, random. And he's got a 58% chance that he doesn't belong in the model. So we would probably want to consider taking that guy out. So that very fact that this is such a high number. Now, is the model any good? Well, if we look at our ANOVA table here, and we look all the way over here, we see that that value is very low. The model is good, but we might want to consider getting rid of this variable. Now let's take a look at one other thing, the r-squared value. Now remember what I mentioned before was that the more variables you put into the model, the better your r-squared value. That's the way it's always going to be. It has more, the linear regression has more to work with, and even if this is random, he can still do something with it. It's not worth anything, but the regression doesn't know that. So he's able to come up with a better model. Look, 85%, 851272. Let's compare that to this guy. So if we come over to this guy, it's 84.9. So if we look at just the r-squared value, 8512, this is a better one. So you would think that this guy here is a better model if you just look at the r-squared. But recall that that when you're comparing different models, you don't look at the r-squared. You look at the adjusted r-squared, because the adjusted r-squared is going to penalize you for putting other variables in the model. So the more variables you put into the model, you get there's a penalty for that. So let's take a look. This is 83.0. And let's take a look at this guy over here, 83.5. So this is a higher value than this guy right here. So we've added a random value and the model got worse. So this is why you look at the adjusted r-squared value. Now, incidentally, it is statistically possible, if we were to keep creating random numbers, every now and then you get lucky. And so if you try this exercise at home and all of a sudden sometimes your adjusted r-squared value actually improves. That will happen on occasion. You know, occasionally you get lucky on these variables, these random variables, and even though you've thrown garbage into the model, you still might improve your adjusted R-squared. So don't look at this as guaranteed to give you the best model. It's just simply a measurement, and sometimes the measurement might give you a false reading that this is a better model. But this is going to occur. These false readings will usually occur especially when you don't have a lot of data to work with. The probability, as you start putting more and more and more data into the model, you know, if I had, instead of right now I have 27, I have 24 records, I think, here. If I have 24,000, the probability that I'm going to get, that this random variable is going to get lucky suddenly becomes a lot less. So one of the things you also have to remember when you're building your predictive models is to exercise common sense. You have to have domain expertise. If you happen to know something about steam plants and you know that random numbers don't predict how much steam you're going to use, then you should probably not put it in. Even if you get a better R-squared, you have to rely on your common sense and your professional judgment. So that is the end of looking at multivariate regression.